Hello, good afternoon to you all students, and this is Jagannadha Rao from Online Gate Coaching 2020. So we start the second session of engineering materials, which comes under manufacturing technology. Okay, yesterday we have seen various types of crystal systems and how to calculate the atomic packing factor and how to calculate density using lattice parameters, and we have solved some problems using lattice parameters, and after that Miller indices, crystallographic directions and crystallographic planes we have seen, and also we have seen crystal imperfections. Okay, and again I am telling you, you better equipped with a pen and a notebook, so to note down various formulae that are used in problem solving. Okay, so today let us start phase diagrams, right? See, let us first see what is an alloy. Alloy is a combination of two or more elements, and at least one is a metal. So that is what we call as an alloy. Okay. So alloy, there must be two constituents or two components, A and B, and at least A or B is a metal, right? So considering, so normally we have roughly about 40 metals, and taking into combination of two, which are binary alloys having two metals, it is a large number, right? And of course, if you go for ternary alloys, there will be three components or three metals, and which are still more number of alloys. But for the present discussion, we restrict ourselves to binary systems. Okay, that is a two-component system. Metal A and metal B is a two-component system. Now, what is a phase diagram? A phase diagram is plotted between the composition of alloy and temperature. So it is a plot. The temperature is plotted against the composition of a alloy. And first of all, in these phase diagrams, let us see a binary equilibrium diagram. So in this binary diagram, we assume that the two components of metals A and B completely soluble in liquid state and completely soluble in solid state, right? They offer complete solubility both in the liquid state or in the solid state. See, when the two components combine in the liquid state, there will be a homogeneous liquid designated by letter L that is there in this figure. And similarly, the two components A and B, when they combine together in the solid state, they form a homogeneous solid solution that is designated by alpha in this phase diagram. And if you see, so at the left hand portion of this diagram, so there is a point where three curves meet. So that is nothing but the melting point of A. And on the right side, there are three lines meeting. So that is the melting point of B. And if you plot a number of cooling curves, so that is the temperature versus time, that is time versus temperature versus time cooling curves, and you can plot the diagram. And liquidus here is at the top of the loop alpha plus L, and this liquidus is a line which indicates the onset of solidification, right? This liquidus gives the onset of solidification, and the solid line gives the completion of the solidification. So in between solidus and liquidus there is a loop, and there is a region in which the liquid and solid coexist, right? And that we can call it a mushy zone, right? So normally a pure metal solidifies at constant temperature, whereas an alloy solidifies over a range of temperature, because the alloys of are having different compositions and they have a solidification range. So that is why you are able to see a loop here, right? A mushy zone, that is a loop in which liquid and solid coexist. So that is a binary equilibrium diagram, and it is also called isomorphous system, in which the two components are soluble, completely soluble in the liquid state and completely soluble in the solid state. Okay. Now let us see. So now here the phase diagram will give the information about the composition of the alloy and what is the amount of liquid present in the alloy at any temperature, and what is the amount of solid that is present at a given temperature at a particular composition, right? So there are two things. You will get the composition of the liquid phase, and you will get the composition of the solid phase, and you will get the percentage of liquid and you will get the percentage of solid. For example, here we see a binary equilibrium diagram. So obviously it has two regions or two regions. One is a liquid, one is a homogeneous liquid, the other one is a homogeneous solid, and there exists a loop in between liquidus and solidus where the liquid and solid coexist, right? Now we want the composition of a particular alloy. How much is the percentage of the liquid and how much is the percentage of solid, and what is its composition? For example, if you take any point in the liquid region, so it is a homogeneous liquid and 100% you will get as a liquid, and the composition of liquid is conforming to the composition of the alloy. And if you take any point in the solid region, it is a complete solid and its composition 100% solid, and its composition is corresponding to the composition of the alloy. But however, it is not so when your point lies within the loop, right? For example, let us say the composition of alloy is W0, that is indicated in this figure, and the temperature at which we want to consider what is the amount of liquid and what is the amount of solid, how much liquid is there, how much solid is there, and what is the percentage of liquid, what is the composition of liquid, and what is the composition of solid, we want to find out. So that means the temperature and the composition of alloy will indicate a point O, which is in the loop. So for this, you draw a tie line parallel to the x-axis passing through the temperature. So that is the horizontal line that is drawn TLS in this diagram. So now this is called a tie line, and this tie line intersects liquid at L and intersects solidus at S. So it intersects liquidus at L and it intersects solidus at S. So now if you want to know the composition of the liquid, so now you drop a perpendicular to the composition axis and it is W1, and W1 WL represents the composition of liquid, and this tie line intersects the solidus at S, and if you drop a perpendicular onto the composition axis you will get the composition of solid. Now we want the percentage of liquid and we want the percentage of solid. Okay, so to get the percentage of liquid, so you use the formula LO by LS into 100 and percentage of solid OS by LS into 100. So using this you can calculate the relative amounts of solid and liquid. Now let us see a eutectic reaction. A eutectic reaction is one in which a liquid separates into two solids, solid 1 and solid 2. See here, if you observe, right, the melting point of A is TA and melting point of B is TB, and you can see the liquidus, and you can you can see the eutectic reaction is occurring at point E. So in the eutectic reaction what happens is the liquid is separated into two solids, solid 1 and solid 2. So that is called a eutectic reaction. So here there are two solids that are precipitating from a homogeneous liquid, and the microstructure of this one appears like this. It is a fine lamellar fingerprint structure which is very strong, right? Normally eutectic structures are very strong. So this is 100% eutectic. So now the alloys to the left of eutectic composition are called hypoeutectic alloys, and the alloys to the right of eutectic composition are called hypereutectic alloys, and above the eutectic temperature in the right hand side, that is in the hypoeutectic region, there will be liquid and A, and similarly on the right hand portion, that is hypereutectic side, you will get the liquid and B, that is above eutectic temperature, and below eutectic temperature it is A and B. But however, hypereutectic alloys contain proeutectic A and eutectic AB. So there are two constituents, proeutectic A and eutectic AB, and on the hypereutectic side, so there is proeutectic B and eutectic A plus B. So that is how the microstructures will appear. Okay. Now let us see. Of course, this is also a eutectic reaction. So here the two solids having some partial solubility in the solid state, right? And here you can see the eutectic reaction, and also you can see the hypoeutectic alloys, and you can see the hypereutectic alloys, and here a solid solution of B in A is called alpha, and a solid solution A in B is called beta. That exists either left and right ends of the phase diagram. Okay. So now peritectic reaction. Peritectic reaction is just opposite to that of eutectic reaction, and here a liquid and a solid combines to form a new liquid. Right here, a liquid and a solid combines to form a new solid. Right, so that is a peritectic reaction. See here in this figure, if you observe this phase diagram, of course there is a homogeneous liquid. At the left hand side there is a solid solution alpha, and at the right hand side below there is a solid solution beta, and there are the two phase regions, liquid plus alpha, liquid plus beta, and alpha plus beta. So these are the various regions present in this diagram. Here at point P, the peritectic reaction is occurring. So here the liquid and the alpha combine to form beta. So that is a peritectic reaction. And here you see there is a liquid and there is alpha, and at point P, at temperature Tp and composition, at this particular peritectic composition, you will get beta. So that is a peritectic reaction. So now let us see eutectoid reaction. Eutectoid reaction is also similar to eutectic reaction, but is occurring at the solid state. And in the eutectoid reaction, solid 1 precipitates into solid 2 and solid 3. Right? So here this is also a eutectic, just like eutectic structure, and here the solid 1, a typical solid 1 is separated into solid 2 and solid 3. So here there are two phases are formed upon cooling, and that is from a solid. If it is a eutectoid reaction, that is from a solid, and if it is a eutectic reaction, that is from a liquid. And the eutectoid structure is also similar to eutectic structure. It is also fine lamellar structure, just like fingerprints, having two phases. Right? It will have two phases, and normally you cannot distinguish a microstructure whether it has come from a eutectic reaction or whether it has come from a eutectoid reaction. Normally, this eutectoid alloys or eutectic alloys are very strong and tough. Okay. Okay. Now let us see the peritectoid reaction. See, peritectoid reaction is reverse of a eutectoid reaction. And here, solid 1 and solid 2, two solids combine to form a new solid. Right? Here, two solids are combined to form a new solid 3. Okay? So it is opposite to a eutectoid reaction. Now let us summarize the invariant reactions in the phase diagrams. So first is a eutectic reaction, so in which liquid is separated into solid 1 and solid 2. So liquid is separated into two solids. And let us think about the eutectoid reaction. In eutectoid reaction, solid 1 is separated into solid 2 and solid 3. In peritectoid reaction, in peritectic reaction, a liquid and a solid combine to form a new solid. And in a peritectoid reaction, solid 1 and solid 2 combine to form a new solid. So those are the invariant reactions. Now let us see iron and iron carbide equilibrium diagram. See, Why to study this diagram? See, iron is a very important engineering material, and iron invariably combines with carbon and forms steels and cast irons, right? So carbon is present interstitially in iron. Of course, iron is a metal and carbon is a non-metal. Okay, but however, they alloys and these are called plain carbon steels or cast irons. Okay, now let us see this iron and iron equilibrium diagram. So here chiefly there are three reactions. So if you observe, at the top there is a small region that is called delta region, and you can observe the melting point of pure iron is 1538 degrees centigrade, and at 1493 degrees centigrade there is a reaction occurring, that is a peritectic reaction, and in which liquid and delta combines to form gamma. So that is a peritectic reaction that is occurring in the delta region, that is the region at the top of this diagram. So at 1493 degrees centigrade, liquid iron plus delta, which is a solid, combine to form a new solid called austenite. This gamma is called as austenite. And also at 727 degrees centigrade, the austenite precipitates into two solids, that is ferrite and cementite. And this is a eutectoid reaction, and in general the eutectoid composition is 0.8% of carbon. And of course there is a eutectic reaction occurring at 1147 degrees centigrade and at 4.3% of carbon. So this is a eutectic reaction in which the liquid is separating into two solids, and those are austenite and cementite. So normally the iron carbon alloys between carbon percentage 0 to 2 are called steels. That means iron carbon alloys with carbon content less than 2% are steels, and above 2% and up to 6.67% of carbon, the alloys are called as cast irons, right? The alloys are called as cast irons. Okay, so that is the difference between steel and cast iron. Okay, now let us see various types of phases that are present in iron carbon alloys, right? Various types of phases that are present in the iron carbon alloys. One is ferrite. Ferrite is a solid solution of alpha iron in carbon, right? Ferrite is a solid solution of alpha iron and carbon. And of course ferrite is magnetic and it is soft and ductile, right? Ferrite is soft and ductile. Okay, and of course the another phase is austenite. Austenite is a solid solution of gamma iron and carbon, right? Austenite is a solid solution of gamma iron and carbon, but however this is non-magnetic, but it is very strong and tough, right? See, when you require softness, you want ferrite, and when you require toughness, you need austenite in steel. So that is how the alloys needs to be designed. And of course there is cementite. The cementite is an interstitial compound of carbon and iron, represented by the chemical formula Fe3C, having fixed percentage of carbon 6.67%, right? See, here you see the cementite is a compound right? The cementite is a compound and it is represented by a definite chemical formula and it has fixed composition. And whereas when you go for a solid solution, solid solutions have a range of composition. Whether it be interstitial solid solution or substitutional solid solution, you have a small range of composition. So those are called solid solutions. So the solid solutions are available over a range of compositions. Your ferrite is a solid solution and your austenite is a solid solution, but however, your cementite is not a solid solution. It is an interstitial compound of carbon and iron represented by the chemical formula Fe3C having fixed percentage of carbon, that is 6.67. But what is the significance of cementite? And the cementite is extremely hard and brittle, right? So it is very extremely hard and brittle. So because of this nature, cementite is used in cutting tools. Because for cutting tools such as a chisel or a saw and so many other things, knives, etc., razors, you require hardness. So that is why for those alloys, cementite has to be in significant quantities. And of course, there is another phase, that is perlite. And this perlite is a eutectoid mixture of ferrite and cementite. And this is a binary structure, it is strong and tough. I told earlier, eutectic mixture and eutectoid mixture are fine lamellar fingerprint like structures. They are extremely strong and tough. And this fingerprint mixture can come from a eutectic reaction or it can come from a eutectoid reaction. But in the case of iron carbon alloys, it has come from eutectoid reaction because it is austenite. So that is separated to form cementite and ferrite. So here you see ferrite is very soft and ductile, is it not? Right? Ferrite is very soft and ductile and cementite is very hard. So this binary alloy, the binary mixture, perlite, is both soft and strong, soft and hot, because cementite is hard. It is both soft and hard, and the combination of soft and hardness in a layer by layer manner, just like a fingerprint structure, makes it strong and tough, right? Makes it strong and tough. So that is why normally when the requirement is toughness and strength, one has to go for perlite. And of course there is another phase that is called leduburite, and this is not having greater significance, and leduburite is a eutectic mixture of austenite and cementite. As you know, this eutectic reaction is occurring roughly about 1150 degrees centigrade, that is relatively high temperature. See, at high temperature, the grain size is coarse. See, as the temperature is reduced, the grain size will decrease. But at higher temperature, the grains tends to be coarse. So the leduburite will not have any significant applications. But of course, this is a unstable phase, and this we can see in the case of cast irons, right? So those are the types of phases that are present in iron carbon alloys. Okay, and the phases one has to remember: ferrite is soft and ductile, and austenite is non-magnetic, strong and tough, and cementate is hard and brittle, perlite is strong and tough, etc. Okay, so if you see the iron carbon diagram at the lower temperatures, that is below 912 degrees centigrade, you will get alpha. More or less alpha, of course, this alpha is limited to a very narrow region. Right? This alpha is a very narrow region. And on the other extreme, the cementate is there at 6.67% of carbon at on the right hand side. So that means as the composition of carbon increases at lower composition levels, you will get ferrite. Relatively very, very small, because the maximum solubility of carbon for iron is very, very limited. It is approximately 0.025% carbon. It is very, very small. Okay. So that is why at lower temperatures and lower carbon contents, you have ferrite. Right? You have ferrite. See, so let us see once again this. See, you know that at 727 degrees centigrade, there is a eutectoid reaction at carbon content 0.8%, and here it is given as 0.676%. So let us see these eutectoid alloys. Let us go back. See, here you can see the eutectoid reaction. See, this eutectoid reaction is solid 1 precipitating into solid 2 and solid 3. And in the context of iron carbon diagram, it is the austenite that is separating into perlite and ferrite and cementite. And it is the austenite that is separating into ferrite and cementite, and the mixture of ferrite and cementite is given a name perlite. That is a eutectoid mixture. And here the eutectoid reaction is occurring at eutectic temperature indicated by TE and eutectic composition E. You can see here. And the alloys to the left of eutectic composition are called hypoeutectic alloys. And the alloys, eutectoid alloys, hypoeutectoid alloys. And the alloys to the right of eutectoid reaction are called hypereutectoid reactions. So likewise, we have this iron carbide diagram at 0.76 or 0.8. We have eutectoid reaction occurring at 727 degrees centigrade. Okay, and the alloys to the left of eutectoid reaction are called hypoeutectoid steels. Right? They are called hypoeutectoid steels, and the alloys to the right of eutectoid reaction are called hypereutectoid steels. So that is the difference we have. And again, go back. Here, if you see a hypoeutectoid alloy, see, within the two-phase region, you have alpha and gamma. Right? We have alpha and gamma, that is a binary structure. And after that, when the gamma reaches the eutectic composition and eutectic temperature, gamma will be again separated into alpha plus beta. But however, there is alpha that is presented, that is precipitated before alpha plus beta, because this alpha plus beta mixture is a eutectoid mixture, right? It is a eutectoid mixture, and this alpha is called pro-eutectoid constituent. And similarly, for a hyper-eutectoid alloy, you have a pro-eutectoid beta and eutectoid alpha plus beta. So there are, of course, there are two phases. One is alpha phase, and the other one is alpha plus beta phase. Remember, here alpha and alpha plus beta. Alpha plus beta is altogether a different phase, and that is your eutectoid phase. And for a hypoeutectoid alloy, we have proeutectoid constituent and eutectoid constituent. And similarly, for the hypereutectoid also, you will have proeutectoid beta and eutectoid alpha plus beta. So when you come to the iron carbon alloys, especially steels, at lower temperatures and in the hypoeutectoid region, you will get, finally at room temperature, you will get alpha and perlite, ferrite and perlite. And if the carbon content is more than 0.8%, you will get cementite and perlite. Understand? So now, as you move away from the eutectoid point, the eutectoid content will decrease and the proeutectoid content will increase. Okay? That is what I want to convey. Okay. Now let us see, we have studied the iron carbide equilibrium diagram. So let us see about the ferrous metals. These ferrous metals are iron based metals, that is what we have seen. And they can be classified as plain carbon steels, which are nothing but alloys of iron and carbon, and alloy steels. See, carbon is a common, most common alloying element in iron, with iron. But however, in alloy steels, you will use alloying element other than carbon. For example, you will use chromium, vanadium, nickel, cobalt, chromium, tungsten, molybdenum, copper, aluminium. So when these quantities are significant in steels, they are called alloy steels. We'll come to that later. And of course, tool steels, right? Tool steels are specifically tool steels that are used for cutting tool applications. And the other kind of iron ferrous materials are cast irons. So in cast irons, you have white cast iron, malleable cast iron, grey cast iron, spheroidal grey cast iron, and chilled cast iron. So these varieties we will see. Of course, in gate, normally you are asked to recognize the composition of a particular alloy or applications of a particular alloy, like that. So that is why this is important. Now let us see plain carbon steels. And these plain carbon steels contain carbon up to 2%. So we have seen on the iron carbon equilibrium diagram, the alloys containing carbon less than 2% are called steels, and more than 2% they are called cast irons. And the plain carbon steels can be divided into three categories. One is low carbon steels, the other one is medium carbon steels, and the other one is high carbon steels. So these are plain carbon steels, just iron allied with carbon. See, always carbon is present in iron, right? So carbon is a very common alloying element, right? So that is why there are plain carbon steels. So in plain carbon steels, low carbon steels, medium carbon steels and high carbon steels. Now let us see the details of them. See, low carbon steels, the content can be up to 0.35%. See, this 0.35 is also high quantity, can be up to 0.3%. And here you have two categories: 8 mild steel between 0.8% and 0.15% carbon. And you have mild steel between 0.15% carbon and 0.35% carbon. See this carbon steel are hypoeutectoid alloys that you can see, and the maximum carbon content can be up to 3%, right? But your eutectoid composition is 0.8. So that means the composition of mild steel, that low carbon steels, are away from the eutectoid steels. So that is why the perlite content is less and ferrite content is more. So that is why I have gone back to tell you what is a pro-eutectoid constituent and what is a eutectoid constituent. See, because the carbon content is about up to 0.35%, the perlite content is very low and the ferrite content is high. Okay, and because the ferrite is high, it will have lot of ductility. The ductility is very high, so that is why these are used to draw wires. Low carbon steels are used to make wires, and they are used to make deep drawn products, that is cups, tumblers, etc. Okay, and of course they are soft and ductile, and however they cannot be hardened by heat treatment, right? They cannot be hardened by heat treatment. Okay, so that is about low carbon steel. Now let us see medium carbon steel. Medium carbon steel contain carbon between 0.3 to 0.6%. Of course, medium carbon steels are also hypoeutectoid steels. So in hypoeutectoid steels, there will be perlite and ferrite, right? Now, as you composition of the carbon is increasing in the medium carbon steel, and its composition tending towards eutectoid steel, so thereby you will get higher perlite content and lower ferrite content. That means they are stronger than the low carbon steels. Because of the high perlite content, they are stronger than the low carbon steels and harder than the low carbon steels. Because ferrite content is becoming low, right? So at the expense of ferrite, we have perlite. Because of the ferrite content is low, the ductility of medium carbon steels is low when compared with low carbon steels. But the strength improves, right? And of course, these medium carbon steels are used as structural steels, right? So normally they are used to make, they are used as structural materials, right? Many structures are built of medium carbon steel, and machine tool, guideways, all these stiffer parts are made of medium carbon steels, and railway wheels, tracks, gears, crankshafts, all are made by medium carbon steels. Now, high carbon steels. In high carbon steels, the carbon content is up to 1.2% carbon. See, the maximum possible carbon content in steel can go up to 2%, but however, commercial steels, the carbon content is limited to 1.2 to 1.4%. It will not be more than 1.2%, right? So the range can be 0.6 to 0.12, right? Say portion or hypoeutectoid, and the other portion also hypereutectoid. Yes. So as perlite content is increased, they become strong, they become hot, and if you see hypereutectoid LIS, the cemented content is increasing. They have become more and more hot. So that is why high carbon steels are relatively hot, right? High carbon steels are relatively hot, and they are used for cutting tool applications such as knives, razors, chisels, etc. So those are the applications of high carbon steels. Now, let us see heat treatment of steels. Of course, there are plain carbon steels, medium carbon steels, low carbon steels, and high carbon steels. They cater for some of the engineering applications. However, the demand of service conditions in engineering application required variety of properties that are not given by plain carbon steels. So for that, the steels are heat treated to improve the mechanical properties of steels, right? The steels are heat treated to improve mechanical properties by the application of heat. So that is called heat treatment, right? That is called heat treatment, and heat treatment is a process of heating and cooling of steel in a controlled manner, right? Heat treatment is nothing but the application of heat. How to apply heat? Either we heat or we cool, and we apply this heating and cooling in a systematic manner to achieve desired properties. So that is what do you mean by heat treatment of steels. Now let us see the types of heat treatment processes. Firstly, there is annealing, right? Annealing. And after that, there is normalizing. So then hardening, then tempering. So these are the four basic heat treatment processes. First one is annealing, and second one is normalizing, third one is hardening, and fourth one is tempering, right? So in annealing, what is done? The steel is heated very slowly, right? The steel components are heated very slowly to the annealing temperature, and after that they are soaked at the annealing temperature so that the temperature becomes homogeneous, and after that they are cooled in systematic manner. Let us see what is that systematic manner later. So that is annealing. So what annealing does, right? So it will relieve the internal stresses. It imparts softness to the steels. That means it restores ductility. For example, when a material is worked, say especially the cold working. So when a material is worked, because of the working, that is the application of force, there is a distortion and residual stresses within the component. And of course, so when you work a material, because of the working of the material resists further working, which is called strain hardening, and this is also called work hardening. That means when a material is worked, say cold worked, that means at lower temperature by the application of force, say by some extrusion or forging like that. Okay. So when you apply the working, so there is distortion, and there are residual stresses, and also because of work hardening, the material loses ductility, right? The material loses ductility. So when you apply an annealing treatment, the distortion is relieved and residual stresses are relieved, and then the ductility is restored. Understand? The ductility is restored. That means annealing softens the component. And what are the different types of annealing processes? First one is full annealing. The second one is process annealing. The next one is stress relief annealing. And the other one is spheroidizing. There are different kinds of annealing processes. One is full annealing. The other one is process annealing. The next one is stress relief annealing. And then spheroidizing. And then normalizing, of course, and hardening. In hardening, there are two varieties, full hardening and case hardening. We'll come to that later. Tempering. So there are different kinds of tempering are there, and our interest is mark tempering and mass tempering. Okay. Now let us see the heat treatment cycles. And this figure shows the heat treatment cycle for annealing and normalizing. See, there are variety of heat treatment cycles. Each cycle there is a heating phase, and there is a soaking phase, and there is a cooling phase. Heating phase is represented by upward arrow, that sloped line, upward arrow, and the soaking is represented by horizontal line, and the cooling is represented by downward arrow. So we have how many processes? We have 1, 2, 3, 4, 5 processes are there, right? 5 processes are there. Let us say first annealing, right? See, annealing, if you see, there are 2 types. So that is annealing for hypoeutectoid steels and annealing for hypereutectoid steels. And let us see the annealing for hypoeutectoid steels. So here the soaking temperature or annealing temperature is very high. That is above A3 or ACM line. What are these 2 lines? Let us see later. See, that means for hypoeutectoid steels, the annealing or the soaking temperature is high as compared to that of hypereutectoid steels. So that means the components are heated very slowly. Why they are heated very slowly? When you heat fast, there may be distortion and residual stresses because of the thermal gradient. Understand? So that is why in any heat treatment process, the heating takes place in a very smooth manner, that is slowly. The heating takes place very slowly up to the annealing temperature. So let us say for this annealing cycle for hypoeutectoid steel, this heating is about 10 hours. And after that, it is soaked at annealing temperature for say 4 hours, right? And after that, it is furnace cooled, right? After that, it is furnace cooled. That means after soaking, you shut off the furnace and allow the components to remain within the furnace and let them cool. So then that cooling process is very, very slow. that is called furnace cooling, and because of furnace cooling you will get the temperature gradients are very small, and the residual stresses are relieved, and then distortion is relieved. It will restore the ductility. Understand? So annealing, there are three stages: heating very slowly and soaking about 4 hours, and furnace cooling. Right? Furnace cooling. And then for hypereutectoid steel, the annealing temperature is less than that of hypereutectoid steel. And you see other curve, anneal, below the anneal. And again here also it is heated slowly to the annealing temperature, and again soaked at the annealing temperature, and then furnace cooled. And this is the treatment that is given for hypereutectoid steels. And let us see why there is a temperature difference for hypereutectoid steels and for hypoeutectoid steel. Let us see later. The processes are same except the annealing temperature. You heat it, right? You heat it slowly and soak it at annealing temperature, and then perform furnace cooling. So what the effect? It will relieve the internal stresses, and it will restore the ductility. It will relieve the distortion. So that is the advantage of annealing. But however, see, most components we do not want ductility. For example, a structural member. A structural member we don't want ductility. So for that, instead of annealing, we do normalizing. Right? For that, instead of annealing, we do normalizing. And normalizing also is similar to annealing process, except the normalizing temperature is slightly more than the annealing temperature. Right? The normalizing temperature is slightly more than the annealing temperature. And here also there are three phases: heating, soaking, followed by air cooling. That means in annealing, the components are cooled inside the furnace, and whereas in normalizing, the components are cooled in air, still air. So when compared to furnace cooling, air cooling is faster. Is it not? Furnace means it is insulated. The cooling is very, very slow. But whereas air offers natural convection. The cooling rate is faster than the furnace cooling. So that is why, because you are cooling it faster, the steel will become stronger. That means if you cool slowly, it will become soft. And when you cool fast, the material will become strong. So that is a normalizing treatment. And of course, there are some more variations of annealing process. First one is process annealing. Process annealing is given after a particular process such as forging. After you forge a material, there will be residual stresses and distortion, and in order to relieve the residual stresses and distortion, you have to process annealing. That is done after a particular process, and here the annealing temperature is very low, roughly about 400 to 500 degrees centigrade. And stress relief annealing. Stress relief annealing is given only to relieve internal stresses. There is no improvement of ductility, and there is no relief of distortion. But however, you are really relieving the stresses. It can be carried out roughly about 300 to 400 degrees centigrade. So in a nutshell, so what is the heat treatment process? It will have three stages. One is slow heating, and after that soaking, and after that cooling. So in annealing, there is slow heating, soaking, and then followed by furnace cooling. And the annealing temperature for hypoelectric steels are more than the annealing temperature of hyperelectric steels. Let us see it later. And normalizing is also having three stages: heating, soaking, followed by air cooling. Right? Normalizing is characterized by air cooling. Right? So, because of this air cooling, the cooling will become faster than the furnace cooling, and you will get a strong component. And process annealing, it is also less than the annealing temperature of hyperelectric or hypoelectric steels, and it is given after a process. And the annealing temperature is approximately 400 to 500 degrees centigrade. And whereas stress relief annealing is done approximately at 300 to 400 degrees centigrade. So that is about heat treatment cycles. Now let us see heat temperature ranges of heat treatment of steels. So if you observe this diagram, and this is the steel portion of iron carbide equilibrium diagram, right? This is the steel portion, right? So here you can see at the top there is austenite. This V loop is austenite, and on the left hand side there is a small loop. So there you have ferrite, and at the right hand side, representing 1.6% carbon, you will have cementite. So now there are 4 lines, right? So that is AC3 is upper critical temperature. AC3 is on the left hand side, and this is upper critical temperature above which austenite is stable, right? So it is the upper critical temperature above which austenite is stable, okay? And AC1 is the temperature at which the eutectroid reaction will take place, okay? And ACM line is cementite line, right? And of course there is a AC31 line, so that is the lower critical temperature of this steel portion. So there are 1, 2, 3, 4 regions, and of course fifth region is the small of alpha. See, annealing, full annealing is represented by grey color, and this grey color, if you see, for hypoelectric steels, the annealing temperature is above the upper critical temperature, slightly above the upper critical temperature, but for hyperelectric steels, it is above the lower critical temperature. Understand? That means earlier also we have seen the annealing temperature of hyperelectric steels is less than that of hypoelectric steels. Why? Because see, in the hyperelectric steels, in this two-phase region, there is gamma and Fe3C. So when you heat steel into this region, this perlite and cementite are dissolved to form gamma and cementite, right? So in this region, at higher temperature, you have gamma and cementite, and the cementite, the presence of cementite makes it very brittle. That means you start cooling from a brittle region, so thereby the steel will become brittle. In the case of hyper-eutectoid steels. So that is why they are not heated over the ACM line. They are heated over the AC31 line. Right? So that is the full annealing temperature of hyper-eutectoid steels. And what about the normalizing temperature? See, generally normalizing temperature is about the annealing temperature, and here the black region represents the normalizing zone, and it is above the annealing temperature and above the upper critical temperatures for hypereutectoid steels and hypereutectoid steels. So that is your black color. Understand? So that is your black color. And of course, you can see the hardening temperature also. And here in annealing, there is one process called spheroidizing. See, for hypereutectoid steel, so during cooling, there is a precipitation of primary cementite. Understand? So in the case of hypereutectoid steel, in the two-phase region, in the single-phase region there is gamma, and in this two-phase region there is gamma plus cementite. So when you cool from this region, there is pro-eutectoid cementite and eutectoid perlite. Because of this pro-eutectoid cementite, it is very brittle, it is harmful. But however, in the spheroidizing process, you will break the cementite network. So when you break the cementite network, the cementite network is divided into spheroids. The cementite, which is normally a flake-like structure, is divided into spheroids, and the spheroids, presence of spheroids makes the structure machinable. Understand? So that is why, in order to improve the machinability of hypereutectoid steels, spheroidizing treatment is given. So in spheroidizing treatment, the cementite network is broken as cementite spheroids. So this can be done by heating and cooling the steel alternatively above the AC31 line. See that black region at the AC31 line, which is spheroidizing anneal, and the steel is cooled alternatively, cooling and heating above AC31 line. Of course, there are so many processes. And you can see the process annealing region right on the left side of this diagram. Okay. So now we have seen annealing and we have seen normalizing, right? And there is a process called hardening. See, hardness is an important property. Hardness is nothing but resistance to indentation, right? Hardness is nothing but resistance to indentation. Especially for the cutting tool applications, you need material to be hot, and for applications like abrasion, when there is abrasion of parts, you need hotness. Understand? So that is why hardening is also an important process. Not only cutting tools, for example, you take loco wheels. Loco wheels are subjected to abrasion. they also should be hardened. So that is why hardening is very important. But however, the hardening obtained by cementite is not sufficient. That means uh, high carbon steels are not sufficient for cutting tool applications. So that means we want still more hardness when compared to high carbon steels. So for that we have to harden the steel. But how to harden the steel? Right? See, you take say a medium carbon steel and heat it to annealing temperature, say 850 degrees centigrade. And after that, you drastically quench it in a water medium, which is at room temperature. That means heat the, for example, take a loco wheel and heat up to the normal means annealing temperature, which is approximately 850 degrees centigrade. And after that, soaking, you quench the loco wheels in a quench bath, that is water bath, that is maintained at room temperature. So when it is immersed, when the loco wheel is immersed in the water, consequently the cooling rate is very high. The cooling is very drastic. Correct? The cooling will become very drastic, and because of that one, the hardness of the material will increase. Right? So when you cool drastically, what happens? So actually, when you are heating this medium carbon steel and taking it to annealing temperature, the material will become austenite. So according to equilibrium diagram, this austenite has to be converted into ferrite and cementite or alpha iron. Understand? But however, austenite is BCC, FCC, and ferrite is BCC. That means FCC has to change into BCC. So that means, so in FCC there is carbon, and the carbon has to come out from this FCC so that it will become BCC. So it needs some time. But however, when you are drastically cooling, there is no sufficient time to austenite FCC to be converted into BCC. Instead, it will be converted to a BCT structure, body centered tetragonal structure called as martensite. So in martensite is a super saturated phase of carbon, super saturated solution of carbon in iron. So that is what is meant by martensite. Okay, and this martensite is extremely hot, and it is hotter than the cementite. And this martensite is a white needle-like structure. That is what you can see under microscope. See, actually, what is the purpose of quenching steel in order to obtain martensite? Right? In order to obtain martensite. So when you form 100% martensite, right? When you form 100% martensite, you will get full hardness. But however, the transformation of austenite, austenite to martensite is time dependent. Understand? The transformation of austenite to martensite is time dependent. సార్ చిన్న బ్రేక్ సార్, తీసుకోవచ్చా? ఓకే ఓకే, నేను ఇప్పుడు ఫోన్ చేస్తాను. హలో సార్, కొంచెం చిన్న బ్రేక్ సార్, మంచినీళ్ళు తాగాలి, గొంతు ఆరిపోతుంది. ఏంటి? ఓకే సార్, థ్యాంక్ యూ సార్, ఇప్పుడు వచ్చేస్తాను 5 minutes. ఓకే. I am resuming, sir. ఏంటి సార్ రేపు ఉంది, రేపు ఆదివారం కదా ఉంది అయినాను. ఓకే సార్, ఉంటాను. ఓకే సార్. ఓకే students, I want a small break. See here, we have seen what is meant by annealing and what is meant by normalizing. Okay, and we are discussing about hardening. See, I told you that the hardness is given by cementite, as in the case of high carbon steels, is not sufficient for many engineering applications, such as when you have abrasion resistance or for cutting tool applications. This hardness is not sufficient. We want more hardness. So for that, we have to adopt a hardening process. And simply telling, the hardening process is also called a quenching process. So in quenching process, the steel is heated to austenitizing temperature and soaked there for some time, and after that it is dropped in a bath of water which is at room temperature, and the component is fully immersed. So in the fully immersed component, in the room temperature, the cooling is very, very drastic. The temperature gradients are very high. So because of this one, the hardness will improve. Then what happens during hardening? See, when you take steel to the austenitizing temperature, everything will become austenite. And austenite is gamma iron. And you know, the packing factor of gamma iron is 0.74. Now, according to equilibrium, after crossing the eutectoid temperature, it has to convert it into BCC, body centered cubic structure, which is ferrite, which is a part of perlite. Okay, and this is BCC, but this is having a packing factor only 0.62, right? That means the wide space from 0.26 has changed to 0.38. That means the wide space has to increase upon normal cooling. From 26% wide space in FCC, it has to go for 38% in BCC. That means the carbon that is entrapped in FCC has to come out in order to make the things BCC. But however, because of the drastic cooling of the quenching process, there is no sufficient time for the carbon to of this structure. So the carbon will be entrapped in the lattice structure. So instead of FCC converting into BCC, because of this rapid diffusion process, what happens is, instead of converting it to BCC, it will be converted to BCT, a body-centered tetragonal structure, which is called martensite. Martensite is a supersaturated solution of carbon in body-centered tetragonal iron, right? And This martensite is very extremely hard structure. It is harder than cementite. And in the microstructure, it appears just like a white needle-like structure. So when you want full hardening, the aim is to produce 100% martensite. But however, the transformation of austenite to martensite is dependent on time. So for this iron and iron carbon diagram is not sufficient. So for this, we have to study TTT curves. I am showing TTT curve of eutectoid steels. See, earlier we are dealing with temperature and composition. There are only two variables, temperature and composition. And here time is also come into picture. And we want to see the transformation of steel with reference to time. That means we have to fix the composition. So for the sake of convenience, let us take eutectoid composition. The same logic can be extended to hypereutectoid composition and hypoeutectoid compositions also. So I am talking only about the eutectoid steel and which is containing 0.8% carbon, right? So this TTT curve is generally having S shape. It is plotted temperature versus time, and this is on the x-axis, which is on the log scale. That means the transformation may take from a few seconds to a few days. The time span is very high. It may be a few seconds or it may be a few days. So that is why it is plotted on a log scale. And this is S curve. And if you can see the shape of this curve on this diagram, for this eutectoid steel, above AE1 austenite is stable, and this austenite is converted to martensite above, below martensite starting temperature, and martensite forms, complete martensite will form at a still lower temperature that you can see in this diagram. And the left hand side we have a nose, right? And this nose separates a region where the austenite is unstable, and the left right hand side of the figure there are the transformation products, right? So in the right hand side there is austenite unstable, and on the other hand, right hand side there are the transformation products. See, so if you cool slowly, right? If you cool extremely slowly, you will get coarse perlite, right? Actually, the austenite is transformed to perlite in the eutectoid reaction, that you know. So when you cool extremely slowly, what happens is the final product will be coarse perlite. Because you are cooling slowly, the grain size will be higher. The grain size will be coarser. Then you will get coarse perlite. And this coarse perlite is having low hardness. And still, if you increase the heating, the cooling rate, then you will get medium perlite. That means the coarseness of the perlite has reduced. As the coarseness, as the fineness of the perlite increases, the hardness improves, right? Consequently, the hardness improves. And still, if you cool more faster, you will get fine perlite. And still more faster, you will get upper or feathery bainite. And still more cooling rate, you will get binate, and still more cooling rate, you will get acicular binate. So these are the transformation products. See, this transformation depends on time. So that is your cooling rate. And according to your cooling rate, the transformation products ranges from coarse perlite to fine or acicular binate. And if you observe, the hardness of the end product increases from top to bottom. That means perlite is soft, binate is hard. You know, perlite is an aggregate of ferrite and cementite, and similarly, binate is also aggregate of perlite and cementite and ferrite. But binate resembles like martite, right? This binate resembles like binate, martensite. But however, when you cross acicular binate range, that means if you increase your cooling rate further, you will end up martensite, right? You will end up martensite. But however, in order to get the full martensite, your cooling rate, your cooling curve should not cross the nose region of the TTT diagram. There is a nose, you can see that nose, right? And your cooling curve should not cut the TTT diagram. Then you will get 100% martensite. That means if your cooling curve will not cut the TTT diagram, you will get 100% martensite. So that means if you cool at such a rate where your cooling rate, your cooling curve touches the nose of the TTT diagram, you are assured of 100% martensite. And this cooling rate is called as critical cooling rate for a particular composition of steel, right? So that is what you mean by critical cooling rate. And our aim in hardening is to produce 100% martensite. So in order to produce 100% martensite, you have to cool at a rate faster than the critical cooling rate. So then only you can realize 100% martensite. Otherwise, softer products will come. That means say 80% martensite and 20% binate, like that. Okay. So because our aim in hardening is to attain 100% martensite, and you have to cool at such a rate which is more than the critical cooling rate, then you will end up forming 100% martensite. Okay. So that is the information that is given by the TTT diagram. It will give the critical cooling rate, and it will also give what are the transformation products at various cooling rates. Okay. హలో, ఓకే సార్, ఇవాళ కంప్లీటెడ్. సార్ ఏమన్నా క్వశ్చన్స్ ఉంటే పంపించమని చెప్పండి. గూగుల్ ఫామ్ పంపిస్తారా?